Okay, let's go back to this figure, all right? All right. The overshoot of the second order system with zero depends entirely is not true, but it does depends on the ratio, this ratio, all right? Which, as I said it again and again, is the ratio between the distance of zero to the imaginary axis and the distance of the pole to the imaginary axis. So the relative positions of zero and pole really matters. And the relative, when we talk about the position, we are talking about the distance with respect to the imaginary axis. So imaginary axis is really a critical boundary, okay? Because after crossing the boundary, okay, the system can go from stable to unstable, okay? Now, if I go further to the leftward of the x-plane, okay, the system, here I'm talking about poles, similarly become more and more stable, okay? And the response of that system similarly become higher and higher, okay? All right? But the zeros, the impact of the zeros compared to the pole seems to operate in the opposite direction. Why is that the case? The very reason why for this to be true is because the amplitude, the magnitude plot of the zeros move in the opposite direction when it compares to the magnitude plot of pole, okay? That is the fundamental reason we have such a distinct difference between the impact of zero and pole. Now, here, we know that the overshoot actually depending on this. For examples, when A becomes smaller, let's take this curve, eta equal to 0.6 as an example. When, let's say, eta omega n is fixed, that is, the location of the pole is fixed. I'm not going to move it to anywhere. But what I'm doing is, let's move my zero closer to the imaginary axis. As a result, the A becomes smaller, and this curve will move along this path. And as it moves along its path, as A decreases, as the zero moves closer to the imaginary axis, the overshoot becomes larger, okay? Now, by contrast, unit cell response overshoot of a standard second order system depends only on damping ratio. And that tells you zero really matters, okay? Because otherwise, when it comes to overshoot, all you have to do is to consider eta. But if you have zero, then the story is different. From this figure, as I said before, damping ratio still has an impact on overshoot. And the general trend remains the same. That is, when you increase the damping ratio, you reduce the overshoot. But the connection between damping ratio and overshoot is now at a more complex, simply because the existence of zero, okay? When the zero is closer to the imaginary axis, this becomes smaller, and the zero dominates the transient response, producing a larger overshoot. That's exactly what we are seeing in this figure. All right, let's move to another topic, okay? Here, we want to talk about feedback control, okay? Now, before this, we talk about time domain properties of control system. We talk about frequency domain properties of control system. we talk about something about the impacts of feedback controls, but not in a systematical framework. And here, I want to switch our attention to feedback control configuration. Remember the basic elements of a feedback controller. Now, for open loop control, what I have is an input, a system. I apply an input and I'll get my output. This is an open loop control system. Now, for feedback control systems, what I have is this feedback closed loop configurations. Now, remember, it has 4 fundamental blocks: process, actuator, controller, and sensor. Okay. Now, what is the major difference between open loop and closed loop? The major difference is that closed loop control system, which is often also referred to as feedback control system, its output arrow is fed to the controller to improve the performance of the system. So one very important philosophy of feedback control is that the system is actually entirely output arrow driven. Okay, this is very important because the only information received by the controller is output arrow. Whatever decision a controller makes, its decision is based entirely and only on output arrow. So one fundamental philosophy of feedback controller, the feedback control system is output arrow driven, output arrow driven, output arrow driven. Okay, why do I want to say that 3 times? Because it is very important, and I want you to remember it, to learn it by heart. Output arrow driven, and that also tells us the importance of output arrow. Okay, because our feedback control depends entirely on output arrow. All right. Now, and by contrast, for open loop control systems, these are systems in which the output has no effect on the control action. Okay, the only thing that matters is the input. Now, while feedback control is formally used for stability, tracking, and regulation, that is, when we set out a feedback control system, we choose our controller, we tune our controller parameters. We want it to have good stability, good tracking performance, and regulation performance. Okay. Now, for tracking, our goal is a moving target. All right. That is, the output is not a set point, but a trajectory. For regulation, the input command is actually a constant. So what we are doing is set point control. That is what we call regularization. Regulation, not regularization. Okay, the underlying need for this function almost always originates from the need of managed uncertainties. So on servers, we want to perform improved speed of response. We want to have better stability. But the very fundamental motivation for feedback control is we want to manage uncertainties. Those uncertainties can come from the environment, okay? And in the system itself over time, because system components ages as time progress, okay? When I use an old component, its functionality, its parameters might not be the same as what it was when it was just delivered from the manufacturer. All right. After all, we are living in an imperfect world, so uncertainties are always there. Okay. Now, 4 fundamental components. Okay, we just mentioned that. Okay. Now, here, after understanding different measures for the speed of response, including time constant, including bandwidth, including measures such as rise time, settling time, and peak time. Now we want to discuss the speed of response requirements between these four components, okay? Because each of these four components represent an independent subsystem, which means because each of them has its own input and its own output. And in the real world, they can actually be represented by differential equations in many cases, okay? So every one of these components has its own dynamics, which means each one of them has its own time constant. It has its own bandwidth, okay? So a common assumption in classical control is that sensor, controller, and actuator have a much smaller time constant than the process, which means compared to this, they can respond much faster than process. Why is that the case? Because process is the thing we want to control. If these components which are used to help me control the process, if their action is much slower than the process itself, then their actions will never be able to catch up the variation of the process, and the control process will not work, right? If you want to control something, you better move faster than the thing you want to control, right? Otherwise, I will not be able to catch up in the first place. If I cannot catch up with the changing conditions of the system I want to control, how can I control that system effectively? So speed is the number one basic requirement. I have to be fast enough, okay? This is the reason why we assume that even they are dynamic systems, we assume the time constant is much smaller than time constant of the process. So when we put them together, these components can be treated, can be approximated as instantaneous systems. And that allows us to treat them as fast ideal components. Ideal component means instantaneous system, so that the process dynamic dominates the closed-loop system behavior. The term dynamic dominates the closed-loop system. Last time, well, we saw this term before in the case of domino pulse, okay? The scenario is not the same, but the concept behind this and the domino pulse are pretty much identical, all right? Now, in most cases, sensor should be the fastest component in a feedback system because feedback depends on timely and accurate measurements. Why is this the case? I wouldn't say it is always the case, but in most cases, you need, among these components, you need sensor to be the fastest. Why? Because as I just emphasized, the entire operation of the feedback control system is built on the concept of arrow-driven, output arrow-driven. If you want to know the output arrow, then of course the output arrow has to be provided by the sensor. Since our feedback system is built entirely upon output arrow, therefore any inaccuracy of the sensor, any time delay of the sensor will have a profound and most likely negative influences on the overall performance of our feedback control system. So this really matters, okay? So in the future, if you really want to build a high performance control systems, I'm not saying controller is not important. I'm not saying actuator is not important, but one of the fundamental things you need to address is the time response. of the actuator. It's like building a personal computer. When setting out this is one of the very unique phenomenon of Taiwan. In Taiwan, when people want to have a personal computer, they don't usually go to the brand manufacturers. In the United States, you want to buy a personal computer, you go to manufacturers such as Dell, such as Hewlett-Packard, okay? These are very well-known manufacturers, and you buy personal computers from them. But in Taiwan, most likely, we go to places like Jianguo Road, okay? And you go to buy motherboard, you go to buy CPU, you go to different store, buy different components, memory chips, one store, hard disk, from the other store, which store give me the best price, I go to that store. And then I assemble them together by myself or ask them to assemble for me, okay? I probably need to pay a small fee to do that, but that's how we Taiwanese buy our personal computers. Now, in buying those computers, in buying those personal computer components, probably the number one consideration is how fast my CPU is. And probably another important consideration is that how fast my graphic card is. How much memory does it have? How much memory space do I have? Okay, but for me, I think one of the most important things is how large and how good my power supply is, because a solid power supply is the foundation of the reliable operations of personal computers. Same thing happened here. A fast and accurate sensor is the very foundation of a high performance control system, okay? I cannot address this importance more enough, okay? Now, the next topic that we want to focus is on output error. Remember, the performance of control systems can be characterized from 4 different aspects. The first thing is you want to put accuracy. You want your system to be as accurate as possible. That is the reason why we talk about output error. The other is, of course, stability. And this has everything to do with the location of the port. It also has something to do with the location of the zeros, because zero has impacts on the relative stability of the system, right? And this next thing we want to talk about is what? Speed, accuracy, robustness. I'm sorry. The other is speed of response, right? That is the reason why we introduce the concept of time concept in the time domain. That is also the reason why we define bandwidth in the frequency domain. And then robustness. Robustness. And things like gain margin and phase margin specify robustness. Here, for the very first time, we want to formally introduce the impact of feedback control on output error. To understand the feedback of the impacts of closed-loop control on output error, we need to compare the output error of feedback control system to the output error of open-loop control system. Okay, let's look at the open-loop control system. All right, this is the process. This is the controller of an open-loop control system. Now, for the time being, let's just restrict our attention to steady-state error of state response. All right, that is a very good starting point to do such a comparison. Okay, now what is the output error? The output error is defined as the difference between the input and the output. Remember, in such a setting, we assume the input is the command. is so-called the target output. And the real output Y sometimes is referred to actual output. So pretty much input is the ideal output and the real output is the actual output, which means the ideal condition is somewhat different from the actual condition, okay? Reality and ideal conditions always, in most cases, are not the same, okay? Now, this is the definition of output arrow. The subscript here, O, represent these arrows, comes from open-loop system, all right? So what is Y? Based on this block diagram, Y is actually R times GC times G, all right? So based on this very definition, this is actually the output arrow for open-loop control system. Now, remember, this output arrow is given in X domain. It can be I can convert it to frequency domain, but what really matters when it comes to steady state arrow is I need to transform this result to time domain because it is in the real world. We watch how system changes its output with respect to time. All right. So how do we do that? Based on this equality. This equation is what we call final value theorems. We saw that before. I sincerely hope you remember. Okay. Nevertheless, okay, let's just use this equation to determine the steady state arrow of open-loop control system. Now, remember that E of X in this case is this. So I simply substitute this term into here. Okay, the X appear here. Remember that Rx in this case is unit step function, which is U of t. And you take Laplace from U of t, what you get is 1 over S. And this is exactly what we have here. Now, if this is the case, then this is cancel out this 1 over S. So what we have is this. Based on final theorems, we need S approach zeros. So I simply replace all these S by 0. This is what I get. So this is actually the unit step response steady state arrow for this open loop system. No matter what process is, no matter what controller is, this is its steady state arrow when it comes to state response. Now, here, remember that by definition, the loop transfer function is the product of GC times G. Okay, let me write them out. That is, for this part, the transfer function is actually L, and is of course the product of GC and G. Okay, this is our loop transfer function. Loop transfer function is very important. Remember, when discussing gain margin and phase margin and phase margin are defined based on the magnitude, based on the amplitude and phase responses of loop transfer function, not the closed loop transfer function, but the loop transfer function. All right. Now we also did this before. Okay, this is the configuration of our feedback control system. If this is the case, then the transfer function of this system, that is the Laplace transform of C with respect to the Laplace transform of R, where C is the output of the feedback system and R is the input of the feedback system, is actually this. All right. Put it in another way, if we multiply both sides by R, this is what I will get. All right. So we will use this result separate times in the later part of this course. Now, for our feedback control system, initially this is the open loop. All right. So now I want to convert its configuration to feedback loop. And this is what I get, all right? Now, the only difference, there are two differences between this diagram and this diagram. The first difference is that here, the root transfer function is simply G. Now, here, the root transfer function is the product of G and GC. The second difference is that in the feedback loop, we have a transfer function H of X, all right? Here, the transfer function H of X is actually 1, okay? So other than that, everything remains the same. So by using this equation, we can determine the transfer function of this closed loop system as this, okay? Now, so by times my input with this closed loop transfer function, the product is the Laplace transform of the output. By definition, the output arrow is defined as the difference of the input and output. That is, if you subtract the output from the input, you get the arrow. You get the output arrow, okay? So what I do next is I simply substitute this y into here and see what happened, okay? So this part is actually this, and this is what I will get, okay? So this is the output arrow of this feedback control system. And this representation is given in the S domain. But since we are carrying, what we need to know is the steady state arrow in the free time domain. So, like what we did for our open loop system, we use the final value theorems to help me determine the steady state arrow in the frequency domain. So, again, I just plug this or substitute this term into this result, okay? So here we go. EC here, it substitute into the final value theorems and appear here. Again, this S cancel out with R of X, all right? So this is what I get, all right? Again, for this part, this is our DC loop gain, okay? So for the open loop system, DC loop gain is this, all right? Okay, now for if I want to have zero steady state arrow, then this thing has to be 1, because if it is 1, then the output arrow will be 0, right? But there is a problem. That is, there are uncertainties, okay? This might be ideal, but the real GC, the real G might not be the same as the one I used in designing this control system, because what I have is a mathematical model for each of those systems, but my mathematical model might not be the same as the real model of the systems. Yeah, it may be the same in the beginning, but as time progresses, as time moves on, the discrepancy between them will become more and more significant, and that will create a problem. Same thing will also happen in the feedback loop control system. But the thing is, it really doesn't that much, because if I want to make this small, okay, all I need to do is increase the DC gain of the controller. Okay, all I need to do is do that. Okay, of course, these two transfer functions might not be the same as my mathematical model, but it really doesn't matter that much, because let's say it's changed by 5%. Let's say this thing changed by 5 or 10%. But the only requirement I need is for them to be large enough. Okay, for example, let's say GC is, let's say, 100. For some reasons, in real application, it dropped to 95. oh, it goes as 120. It really doesn't that much because 1 divided by 95 versus 1 divided by 100 is, when it comes to the output error, we still have sufficiently small output error, all right? Provided that the DC loop gain is large enough, okay? I don't need this. I don't need this DC loop gain to be any particular number. All I need is them to be large enough. Therefore, there is a plenty of room to tolerate variations, to tolerate uncertainties, because this condition of requiring this term to be large enough is easy to satisfy. It's relatively insensitive to uncertainties. All right, now let us look at a real examples. Here, what we have for the system or process to be controlled is a first order system. Now, let me take a very short break. I need to drink some water for me to go on. All right. Now, let me assume my controller is also a first order system. Remember, this is something I cannot change. This is given. This is the problem. I'm sorry, this is the system or the object or the process I need to control. So there is no freedom in changing g of x because it represents a given system. This is a machine I need to control, okay? Whatever that machine is, I have to deal with it. Okay, I cannot replace it with another machine. However, what I can do is choose my own controller. Let me choose this to be my controller. And the next thing I need to do is to tune these parameters. Okay, I can choose the value for Ka. I can choose the value for tau, which is apparently the time constant of this first order system. Now, let's look at the arrow, okay, the output arrows. Now, for the open loop system, the output arrow is simply this, because GC0 is simply Ka, right? When this goes to 0, this is nothing but the Ka. Similarly, for this term, when g of x, when x is equal to 0, this go away. So all I have left is k. So this is the output arrow. In order to have 0 output arrow, what I need to do is I can set Ka to be 1 over k. Then it will be 0, okay? And it looks ideal. And this is a process, this process is sometimes referred to calibration. You calibrate your controller, the parameters of controller, to satisfy the design requirements. And here, the design requirement is 0 steady state error, right? But as I said before, K can change with time. Even Ka can change with time. So this requirement might be able to satisfy these requirements in the beginning, but as time progresses, when I put it in the real world, this condition can be easily violated. Now, let's go to the feedback control system, okay? This is the output arrow of the feedback control system. Now, again, we already know the loop transfer function is Ka over K. So this is the output arrow of the closed loop feedback system. Here, all I need to do is to make Ka sufficiently large, okay? So when it is sufficiently large, then this number is sufficiently large. When it is sufficiently large, it means the output error is sufficiently small. Whatever parameter variation I have here doesn't matter that much. because all I need to have is for them, that is the product of K and Ka, which come from the process and the controller, to be sufficiently large. And therefore, a very safe choice is choose a very large, choose AKA to be a very large number, okay? So key takeaways for this slide is that steady error is determined by DC loop gain, right? DC loop gain, DC loop gain, okay? Now, these are the mathematical results which clearly show you that steady state error depends on DC loop gain. But what is the reason behind it? Why is that the case? Why does this conclusion make sense? This conclusion makes sense is when you look at this configuration, all right? This, or even this configuration, DC loop gain represents the transfer function of these three subsystems, all right? So when error comes in, the error is processed by this transfer function, okay? So how will the output react really depends on the error and the loop transfer function, right? There is nothing come between them. Error, loop transfer function, output. So the output error depends on loop transfer function, because loop transfer function will change the output according to the output error information it received, all right? So steady error is determined by DC loop gain. Closed-loop feedback can significantly improve accuracy, right? By using very large DC gain value for the controller. For first-order system, increasing controller gain reduces error, apparently. A large loop gain produces large feedback corrective action, all right? Because as we see in this diagram, this is error, this is the output error. A large loop gain means the controller will, based on this error, generate a stronger corrective action, all right? The larger the loop gain is, the larger the corrective action. And by providing a stronger corrective action, it can more effectively reduce the error, or reducing error more aggressively. Now, this is all good, right? Okay, you have error, I corrected. Okay, the larger my loop gain is, the more aggressive my corrective action is. However, increasing the gains also reduces stability margins, and may cause oscillation and instability. There are side effects. We will talk about those side effects later. Now, remember that the fundamental reason of using feedback controls is to deal with uncertainties. And in the beginning of this course, we have told you that there are basically three types of uncertainties, which are input disturbances, parameter variation, and noise. Now, what I want to do next is to systematically investigate the impact of these uncertainties on output error. Okay. Now, remember that there are four basic components in our system. All right. So here we have three different noise. Okay. So closed-loop controls aims to achieve ideal output despite various uncertainties. One is input disturbance, which enters here. The other is measurement noise, which enters here. The third one is the parameter variation. It does not enter the system. It's come with the process, all right? Now, actually, when it comes to the input disturbance, to be more precise, the input, I should put a junction here, and the input disturbance really enter here. Okay. TUR. I'm sorry. Okay. Now, this force applied to the robot represent a type of input disturbance, and this heavy payload endured by this vehicle represent parameter variation. Okay, so as you can see in the real world, parameter variation as well as input disturbances pretty much exist everywhere. Now the third thing is about measurement errors, which come from measurement noise. Now let me emphasize again: a sensor serves as the control system's eyes, and its accuracy and response time are critical to the overall performance of the system. That is the reason why not long ago, I told you that among these four fundamental components, in most cases, we need the sensor to be the fastest component, okay? It has to be faster than the actuator, then the controller, and then the process, of course. Now, remember that what I want to do here is to investigate the impacts of these disturbances on the output arrow, okay? Here, I assume the process to be G, okay? And the controller to be GC, all right? So when you put them together, this is my loop transfer function. And here, I assume H to be 1, which means I'm dealing with unity feedback, okay? Now, the output is actually determined by 3 inputs. The impact of the nominal input represent these components, okay? And the impact of the input disturbance appear here. And the impact of the measurement noise on the output appear here, okay? Now, we know where this come from, but where do these 2 terms come from? Well, it is actually very easy. It's all based on this equation, all right? Now, let's first look at this term, all right? Now, one way to look at this system is that this is the output, and this system actually had 3 inputs. This one is the nominal input, okay? This one is an input that we don't want, an undesirable input, which is input disturbance. And this is the certain input, which is the measurement noise. So when you view this as an output, you actually have 3 different kinds of inputs. The differences lie on 2 conditions, 2 different aspects. The first thing is the nature of the difference. This is the nominal input, this is the disturbance, this is measurement noise. But the next difference is as inputs that enter the system at different location or different spots, all right? Now, for the nominal input, this is our feedback control system. So we saw this before. This is the transfer function between R and Y. Now, with H equal to 1, and let's now assume this to be 0, and this also to be 0, then I can redraw this block diagram by treating TD as my input. What will happen is that if this is the input, it will first encounter the process, and the output will be Y, all right? So that's exactly what we have here. TD is here. It encounters the process, and the output become Y. Now, the output then goes through the controller. Why? Because if you're following this task, this is exactly what the case. Input disturbance enter the system. It first encounters the process, and the output of process is actually the output of the system. And then the Y goes to the controller, right? Remember this, there is a minus signs, okay? So this is exactly the case. Times GC and the minus signs. And then it joins with the input disturbance, right? I'm sorry. Here, TD times GC become Y, and then times minus, I'm sorry, and times minus 1, and then times GC, and then it join TD, right? So this is the block diagram by treating TD as input and Y as the output. Now, for this feedback control system, by using, again, this equation, which is the result of this block diagram, we can determine the transfer function between input disturbance and output. That is a very systematical approach to demonstrate, to help us understand the impact of the input on the output, all right? Because we know their interaction by establishing the transfer function between them, all right? Now, we can do the same thing to the measurement noise. That is, we assume H to be 1, we assume this to be 0, we assume T to be 0, and H will go here with a minus 1. So, I'm sorry, N noise, not H. Okay, measurement noise. The first thing it counted is minus signs, and then it times GC, and then it times G, and then it become Y, and then it join the measurement noise, okay? And this is exactly the case. Initially, the minus signs come from the, here, all right? So I have minus in here, and it will run into GC first, and it will encounter G later, right? Here, minus sign run into GC first, and then encounter G next, all right? And then it becomes Y, right? And then Y will join with minus M, all right? So this is the block diagram for the transfer function model between minus M. Remember, N is the measurement noise and the output. So this represents the dynamics between noise and output. That is the reason why we have this, okay? Okay. So the next thing, apparently, what we need to do is to understand the impacts of these uncertainties on the output, all right? Now, we already know what Y is when we have input disturbance and measurement noise. So by definition, the arrow is always defined as the difference between the input and output. So since I already have the output given here, so based on the definition, I can easily derive the arrow of the system, all right? So as you can see, the arrow really can be decoupled into 3 different terms. One is related to nominal input. The other is caused by input disturbance. And the third is determined by the measurement noise. Okay, time is up. Thank you again for your participation. One more week to go. I hope to see all of you next week. All right.